And because these local derivatives, like dt by dc, are just 1, we basically just copy over dl by dd, because this is just times 1. So what is it? So because dl by dd is negative 2, what is dl by dc? Well, it's the local gradient, 1.0, times dl by dt, which is negative 2. So literally what a plus node does, you can look at it that way, is it literally just routes the gradient, because the plus node's local derivatives are just 1. And so in the chain rule, 1 times dl by dd is just dl by dd. And so that derivative just gets routed to both c and to e in this case. So basically, we have that e dot grad, or let's start with c, since that's the one we've looked at, is negative 2 times 1, negative 2. And in the same way, by symmetry, e dot grad will be negative 2. That's the claim. So we can set those, we can redraw, and you see how we just assign negative 2, negative 2? So this backpropagating signal, which is carrying the information of like what is the derivative of L with respect to all the intermediate nodes, we can imagine it almost like flowing backwards through the graph, and a plus node will simply distribute the derivative to all the leaf nodes, to all the children nodes of it. So this is the claim, and now let's verify it. So let me remove the plus h here from before. And now instead what we want to do is we want to increment c. So c dot data will be incremented by h. And when I run this, we expect to see negative 2. Negative 2. And then of course for e, so e dot data plus equals h, and we expect to see negative 2. Simple. So those are the derivatives of these internal nodes. And now we're going to recurse our way backwards again. And we're again going to apply the chain rule. So here we go, our second application of chain rule, and we will apply it all the way through the graph. We just happen to only have one more node remaining. We have that dl by de, as we have just calculated, is negative 2. So we know that. So we know the derivative of L with respect to e. And now we want dl by dA, right? And the chain rule is telling us that that's just dl by de, negative 2, times the local gradient. So what is the local gradient? Basically de by dA. We have to look at that. So I'm a little times node inside a massive graph, and I only know that I did a times b, and I produced an e. So now what is dE by dA and dE by dB? That's the only thing that I sort of know about. That's my local gradient. So because we have that E is A times B, we're asking what is dE by dA? And of course we just did that here. We had a times, so I'm not going to rederive it. But if you want to differentiate this with respect to A, you'll just get B, right? The value of B, which in this case is negative 3.0. So basically we have that dl by dA. Well, let me just do it right here. We have that a dot grad, and we are applying chain rule here, is dl by de, which we see here is negative 2, times, what is dE by dA? It's the value of B, which is negative 3. That's it. And then we have b dot grad, is again dl by de, which is negative 2, just the same way, times, what is dE by dB? Is the value of A, which is 2.0. That's the value of A. So these are our claimed derivatives. Let's redraw. And we see here that A dot grad turns out to be 6, because that is negative 2 times negative 3. And B dot grad is negative 4 times, is negative 2 times 2, which is negative 4. So those are our claims. Let's delete this and let's verify them. We have A here, A dot data plus equals H. So the claim is that A dot grad is 6. Let's verify. 6. And we have B dot data plus equals h. So nudging b by h and looking at what happens, we claim it's -4, and indeed it's -4, plus minus, again, float, oddness, and that's it. That was the manual backpropagation all the way from here to all the leaf nodes. And we've done it piece by piece, and really all we've done is, as you saw, we iterated through all the nodes one by one and locally applied the chain rule. We always know what is the derivative of L with respect to this little output, and then we look at how this output was produced. This output was produced through some operation, and we have the pointers to the children nodes of this operation. And so in this little operation, we know what the local derivatives are, and we just multiply them onto the derivative always. So we just go through and recursively multiply on the local derivatives. And that's what backpropagation is. It's just a recursive application of chain rule backwards through the computation graph. Let's see this power in action just very briefly. What we're going to do is we're going to nudge our inputs to try to make L go up. So in particular, what we're doing is we want a.data, we're going to change it. And if we want L to go up, that means we just have to go in the direction of the gradient. So a should increase in the direction of gradient by like some small step amount. This is the step size. And we don't just want this for B, but also for B, also for C, also for F. Those are leaf nodes, which we usually have control over. And if we nudge in direction of the gradient, we expect a positive influence on L. So we expect L to go up positively. So it should become less negative. It should go up to say -6 or something like that. It's hard to tell exactly. And we'd have to rerun the forward pass. So let me just do that here. This would be the forward pass. F would be unchanged. This is effectively the forward pass. And now if we print L.data, we expect, because we nudged all the values, all the inputs in the direction of gradient, we expected a less negative L. We expect it to go up. So maybe it's -6 or so. Let's see what happens. Okay, -7. And this is basically one step of an optimization that will end up running. And really this gradient just gives us some power because we know how to influence the final outcome. And this will be extremely useful for training neural nets, as we'll soon see. So now I would like to do one more example of manual backpropagation using a bit more complex and useful example. We are going to backpropagate through a neuron. So we want to eventually build out neural networks. And in the simplest case, these are multilayer perceptrons, as they're called. So this is a 2-layer neural net. And it's got these hidden layers made up of neurons, and these neurons are fully connected to each other. Now, biologically, neurons are very complicated devices, but we have very simple mathematical models of them. And so this is a very simple mathematical model of a neuron. You have some inputs, x's, and then you have these synapses that have weights on them. So the w's are weights. And then the synapse interacts with the input to this neuron multiplicatively. So what flows to the cell body of this neuron is w times x. But there's multiple inputs, so there's many w times x's flowing into the cell body. The cell body then has also like some bias. So this is kind of like the innate sort of trigger happiness of this neuron. So this bias can make it a bit more trigger happy or a bit less trigger happy regardless of the input. But basically we're taking all the w times x of all the inputs, adding the bias, and then we take it through an activation function. And this activation function is usually some kind of a squashing function, like a sigmoid or 10H or something like that. So as an example, we're going to use the 10H in this example. NumPy has a np.10H, so we can call it on a range, and we can plot it. This is the 10H function, and you see that the inputs, as they come in, get squashed on the y coordinate here. So right at 0, we're going to get exactly 0. And then as you go more positive in the input, then you'll see that the function will only go up to 1 and then plateau out. And so if you pass in very positive inputs, we're going to cap it smoothly at 1. And on the negative side, we're going to cap it smoothly to -1. So that's 10H. And that's the squashing function or an activation function. And what comes out of this neuron is just the activation function applied to the dot product of the weights and the inputs. So let's write one out. I'm going to copy paste because I don't want to type too much. But okay, so here we have the inputs x1, x2. So this is a two-dimensional neuron. So two inputs are going to come in. These are thought of as the weights of this neuron. Weights W1, W2. And these weights, again, are the synaptic strengths for each input. And this is the bias of the neuron, B. And now what we want to do is, according to this model, we need to multiply x1 times W1 and x2 times W2. And then we need to add bias on top of it. And it gets a little messy here, but all we are trying to do is x1 W1 plus x2 W2 plus B. And these are multiplied here. Except I'm doing it in small steps so that we actually have pointers to all these intermediate nodes. So we have x1 W1 variable, x2 W2 variable, and I'm also labeling them. So N is now the cell body raw activation without the activation function for now. And this should be enough to basically plot it. So draw dot of N gives us x1 times W1, x2 times W2 being added. Then the bias gets added on top of this. And this N is this sum. So we're now going to take it through an activation function. And let's say we use the tanh so that we produce the output. So what we'd like to do here is we'd like to do the output, and I'll call it O, is n dot tanh. Okay, but we haven't yet written the tanh. Now, the reason that we need to implement another tanh function here is that tanh is a hyperbolic function, and we've only so far implemented a plus and a times, and you can't make a tanh out of just pluses and times. You also need exponentiation. So tanh is this kind of a formula here. You can use either one of these, and you see that there's exponentiation involved, which we have not implemented yet for our low value node here. So we're not going to be able to produce tanh yet, and we have to go back up and implement something like it. Now, one option here is we could actually implement exponentiation, right? And we could return the exp of a value instead of a tanh of a value. Because if we had exp, then we have everything else that we need. So because we know how to add and we know how to add and we know how to multiply, so we'd be able to create tanh if we knew how to exp. But for the purposes of this example, I specifically wanted to show you that we don't necessarily need to have the most atomic pieces in this value object. We can actually create functions at arbitrary points of abstraction. They can be complicated functions, but they can be also very, very simple functions like a plus. And it's totally up to us. The only thing that matters is that we know how to differentiate through any one function. So we take some inputs and we make an output. The only thing that matters, it can be arbitrarily complex function, as long as you know how to create the local derivative. If you know the local derivative of how the inputs impact the output, then that's all you need. So we're going to cluster up all of this expression, and we're not going to break it down to its atomic pieces. We're just going to directly implement tanh. So let's do that. Def tanh, and then out will be a value of, and we need this expression here. So let me actually copy paste. Let's grab n, which is a sub.theta, and then this, I believe, is the tanh. Math.exp of n minus 1 over 2n plus 1. Maybe I can call this x, just so that it matches exactly. Okay, and now this will be t, and children of this node, there's just one child, and I'm wrapping it in a tuple, so this is a tuple of one object, just self, and here the name of this operation will be tanh, and we're going to return that. Okay, so now values should be implementing tanh, and now we can scroll all the way down here and we can actually do n.tanh, and that's going to return the tanh output of n. And now we should be able to draw it out of O, not of n. So let's see how that worked. There we go. N went through tanh to produce this output. So now tanh is a sort of our little micrograd supported node here as an operation. And as long as we know the derivative of tanh, then we'll be able to backpropagate through it. Now let's see this tanh in action. Currently it's not squashing too much because the input to it is pretty low. So if the bias was increased to say 8, then we'll see that what's flowing into the tanh now is 2, and tanh is squashing it to 0.96. So we're already hitting the tail of this tanh, and it will sort of smoothly go up to 1 and then plateau out over there. Okay, so now I'm going to do something slightly strange. I'm going to change this bias from 8 to this number, 6.88, etc. And I'm going to do this for specific reasons because we're about to start backpropagation, and I want to make sure that our numbers come out nice. They're not like very crazy numbers, they're nice numbers that we can sort of understand in our head. Let me also add O's label. O is short for output here. So that's the R. Okay, so 0.88 flows into tanh, comes out 0.7, so on. So now we're going to do backpropagation, and we're going to fill in all the gradients. So what is the derivative O with respect to all the inputs here? And of course, in a typical neural network setting, what we really care about the most is the derivative of these neurons on the weights specifically, the W2 and W1, because those are the weights that we're going to be changing part of the optimization. And the other thing that we have to remember is here we have only a single neuron, but in a neural net you typically have many neurons and they're connected. So this is only like one small neuron, a piece of a much bigger puzzle, and eventually there's a loss function that sort of measures the accuracy of the neural net, and we're backpropagating with respect to that accuracy and trying to increase it. So let's start off backpropagation here in the end. What is the derivative of O with respect to O? The base case, sort of, we know always, is that the gradient is just 1.0. So let me fill it in, and then let me split out the drawing function here. And then here, cell clear this output here. Okay. So now when we draw O, we'll see that that grad is 1. So now we're going to backpropagate through the tanh. So to backpropagate through tanh, we need to know the local derivative of tanh. So if we have that O is tanh of n, then what is do by dn? Now what you could do is you could come here and you could take this expression and you could do your calculus derivative taking, and that would work. But we can also just scroll down Wikipedia here into a section that hopefully tells us that derivative d by dx of tanh of x is any of these. I like this one, 1 minus tanh squared of x. So this is 1 minus tanh of x squared. So basically what this is saying is that do by dn is 1 minus tanh of n squared. And we already have tanh of n, it's just O. So it's 1 minus O squared. So O is the output here. So the output is this number. O dot data is this number. And then what this is saying is that do by dn is 1 minus this squared. So 1 minus O dot data squared is 0.5 conveniently. So the local derivative of this tanh operation here is 0.5. And so that would be do by dn. So we can fill in that n dot grad is 0.5. We'll just fill it in. So this is exactly 0.5, 1/2. So now we're going to continue the backpropagation. This is 0.5, and this is a plus node. So how is backprop going to, what is backprop going to do here? And if you remember our previous example, a plus is just a distributor of gradient. So this gradient will simply flow to both of these equally. And that's because the local derivative of this operation is 1 for every one of its nodes. So 1 times 0.5 is 0.5. So therefore, we know that this node here, which we called this, its grad is just 0.5. And we know that b dot grad is also 0.5. So let's set those and let's draw. So those are 0.5. Continuing, we have another plus. 0.5, again, we'll just distribute it. So 0.5 will flow to both of these. So we can set theirs. x2w2 as well. That grad is 0.5 as well. And let's redraw. Pluses are my favorite operations to backpropagate through because it's very simple. So now what's flowing into these expressions is 0.5. And so really, again, keep in mind what the derivative is telling us at every point in time along here. This is saying that if we want the output of this neuron to increase, then the influence on these expressions is positive on the output. Both of them are positive contribution to the output. So now backpropagating to x2 and w2 first. This is a times node. So we know that the local derivative is, the other term. So if we want to calculate x2.grad, then can you think through what it's going to be? So x2.grad will be w2.data times this x2w2.grad, right? And w2.grad will be x2.data times x2w2.grad, right? So that's the little local piece of chain rule. Let's set them and let's redraw. So here we see that the gradient on our weight 2 is 0 because x2's data was 0, right? But x2 will have the gradient 0.5 because data here was 1. And so what's interesting here, right, is because the input x2 was 0, then because of the way the times works, of course, this gradient will be 0. And think about intuitively why that is. Derivative always tells us the influence of this on the final output. If I wiggle w2, how is the output changing? It's not changing because we're multiplying by 0. So because it's not changing, there is no derivative, and 0 is the correct answer because we're squashing it at 0. And let's do it here. 0.5 should come here and flow through this times. And so we'll have that x1.grad is, can you think through a little bit what this should be? The local derivative of times with respect to x1 is going to be w1. So w1's data times x1 w1.grad, and w1.grad will be x1.data times x1 w1.grad. Let's see what those came out to be. So this is 0.5, so this would be negative 1.5, and this would be 1. And we've backpropagated through this expression. These are the actual final derivatives. So if we want this neuron's output to increase, we know that what's necessary is that W2, we have no gradient. W2 doesn't actually matter to this neuron right now, but this neuron, this weight, should go up. So if this weight goes up, then this neuron's output would have gone up, and proportionally, because the gradient is 1. Okay, so doing the backpropagation manually is obviously ridiculous, so we are now going to put an end to this suffering, and we're going to see how we can implement the backward pass a bit more automatically. We're not going to be doing all of it manually out here. It's now pretty obvious to us by example how these pluses and times are backpropagating gradients. So let's go up to the value object, and we're going to start codifying what we've seen in the examples below. So we're going to do this by storing a special self.backward and underscore backward. And this will be a function which is going to do that little piece of chain rule. At each little node that took inputs and produced output, we're going to store how we are going to chain the outputs gradient into the inputs gradients. So by default, this will be a function that doesn't do anything. And you can also see that here in the value in micrograd. So we have this backward function. By default, doesn't do anything. This is an empty function. And that would be sort of the case, for example, for a leaf node. For a leaf node, there's nothing to do. But now, when we're creating these out values are an addition of self and other. And so we'll want to set outs backward to be the function that propagates the gradient. So let's define what should happen. And we're going to store it in a closure. Let's define what should happen when we call outsgrad. For an addition, our job is to take outsgrad and propagate it into selfsgrad and other.grad. So basically we want to set self.grad to something, and we want to set others.grad to something. Okay? And the way we saw below how chain rule works, we want to take the local derivative times the sort of global derivative, I should call it, which is the derivative of the final output of the expression with respect to out's data. With respect to out. So the local derivative of self in an addition is 1.0. So it's just 1.0 times out's grad. That's the chain rule. And others.grad will be 1.0 times outgrad. And what you're seeing here is that outsgrad will simply be copied onto selfsgrad and othersgrad, as we saw happens for an addition operation. So we're going to later call this function to propagate the gradient, having done an addition. Let's now do the multiplication. We're going to also define that backward. And we're going to set its backward to be backward. And we want to chain outgrad into self.grad and others.grad. And this will be a little piece of chain rule for multiplication. So we'll have, so what should this be? Can you think through? So what is the local derivative here? The local derivative was others.data, and then others.data, and then times out.grad. That's chain rule. And here we have self.data times out.grad. That's what we've been doing. And finally here for 10h, that backward. And then we want to set outs backwards to be just backward. And here we need to backpropagate. We have out.grad, and we want to chain it into self.grad. And self.grad will be the local derivative of this operation that we've done here, which is 10h. And so we saw that the local gradient is 1 minus the 10h of x squared, which here is t. That's the local derivative, because t is the output of this 10h. So 1 minus t squared is the local derivative, and then the gradient has to be multiplied because of the chain rule. So outgrad is chained through the local gradient into self.grad. And that should be basically it. So we're going to redefine our value node. We're going to swing all the way down here. And we're going to redefine our expression. Make sure that all the grads are 0. Okay? But now we don't have to do this manually anymore. We are going to basically be calling the dot backward in the right order. So first we want to call oats dot backward. So O was the outcome of 10h, right? So calling those O's backward will be this function. This is what it will do. Now we have to be careful because there's a times out.grad, and out.grad, remember, is initialized to 0. So here we see grad 0. So as a base case, we need to set oath.grad to 1.0 to initialize this with 1. And then once this is 1, we can call o.backward, and what that should do is it should propagate this grad through 10h. So the local derivative times the global derivative, which is initialized at 1. So this should dough. So I thought about redoing it, but I figured I should just leave the error in here because it's pretty funny. Why is NumTyObject not callable? It's because I screwed up. We're trying to save these functions, so this is correct. This here, we don't want to call the function because that returns none. These functions return none. We just want to store the function. So let me redefine the value object. And then we're going to come back in, redefine the expression, draw a dot. Everything is great. O.grad is 1. O.grad is 1. And now this should work, of course. Okay, so O.backward should have, this grad should now be 0.5 if we redraw. And if everything went correctly, 0.5. Yay! Okay, so now we need to call ens.grad. Ens.backward, sorry. Ens backward. So that seems to have worked. So ens.backward routed the gradient to both of these. So this is looking great. Now we could of course call b.backward, sorry. What's going to happen? Well, b doesn't have a backward. B's backward, because b is a leaf node, b's backward is by initialization the empty function. So nothing would happen, but we can call it on it. But when we call this one, it's backward, then we expect this 0.5 to get further routed, right? So there we go, 0.5, 0.5. And then finally, we want to call it here on x2, w2, and on x1, w1. Let's do both of those. And there we go. So we get 0, 0.5, negative 1.5, and 1, exactly as we did before. But now we've done it through calling that backward sort of manually. So we have one last piece to get rid of, which is us calling _backward manually. So let's think through what we are actually doing. We've laid out a mathematical expression, and now we're trying to go backwards through that expression. So going backwards through the expression just means that we never want to call a dot backward for any node before we've done sort of everything after it. So we have to do everything after it before we're ever going to call dot backward on any one node. We have to get all of its full dependencies, everything that it depends on has to propagate to it before we can continue backpropagation. So this ordering of graphs can be achieved using something called topological sort. So topological sort is basically a laying out of a graph such that all the edges go only from left to right, basically. So here we have a graph, it's a directly acyclic graph, a DAG, and this is two different topological orders of it, I believe, where basically you'll see that it's a laying out of the nodes such that all the edges go only one way, from left to right. And implementing topological sort, you can look in Wikipedia and so on. I'm not going to go through it in detail. But basically, this is what builds a topological graph. We maintain a set of visited nodes, and then we are going through, starting at some root node, which for us is O. That's where we want to start the topological sort. And starting at O, we go through all of its children, and we need to lay them out from left to right. And basically this starts at O. If it's not visited, then it marks it as visited, and then it iterates through all of its children and calls build topological on them. And then after it's gone through all the children, it adds itself. So basically this node that we're going to call it on, like say O, is only going to add itself to the topo list after all of the children have been processed. And that's how this function is guaranteeing that you're only going to be in the list once all of your children are in the list, and that's the invariant that is being maintained. So if we build topo on O and then inspect this list, we're going to see that it ordered our value objects, and the last one is the value of 0.707, which is the output. So this is O, and then this is N, and then all the other nodes get laid out before it. So that builds the topological graph. And really what we're doing now is we're just calling dot underscore backward on all of the nodes in a topological order. So if we just reset the gradients, they're all 0. What did we do? We started by setting O.grad to be 1. That's the base case. Then we built the topological order. And then we went for node in reversed of topo. Now, in the reverse order, because this list goes from, we need to go through it in reversed order. So starting at O, node backward. And this should be it. There we go. Those are the correct derivatives. Finally, we are going to hide this functionality. So I'm going to copy this, and we're going to hide it inside the value class because we don't want to have all that code lying around. So instead of an underscore backward, we're now going to define an actual backward. So that backward without the underscore. And that's going to do all the stuff that we just derived. So let me just clean this up a little bit. So we're first going to build a topological graph starting at self. So build topo of self. We'll populate the topological order into the topo list, which is a local variable. Then we set self.grad to be 1. And then for each node in the reversed list, so starting at us and going to all the children, underscore backward. And that should be it. So save. Come down here, redefine. Okay, all the grads are 0. And now what we can do is O.backward without the underscore. And there we go. And that's backpropagation. At least for 1 neuron. Now we shouldn't be too happy with ourselves actually, because we have a bad bug. And we have not surfaced the bug because of some specific conditions that we have to think about right now. So here's the simplest case that shows the bug. Say I create a single node A, and then I create a B that is A plus A, and then I call backward. So what's going to happen is A is 3, and then B is A plus A, so there's 2 arrows on top of each other here. Then we can see that B is, of course, the forward pass works. B is just A plus A, which is 6. But the gradient here is not actually correct, that we calculated automatically. And that's because, of course, just doing calculus in your head, the derivative of B with respect to A should be 2. 1 plus 1. It's not 1. Intuitively, what's happening here, right? So B is the result of A plus A, and then we call backward on it. So let's go up and see what that does. B is a result of addition, so out is B. And then when we call backward, what happened is self.grad was set to 1, and then other.grad was set to 1. But because we're doing A plus A, self and other are actually the exact same object. So we are overriding the gradient. We are setting it to 1, and then we are setting it again to 1. And that's why it stays at 1. So that's a problem. There's another way to see this in a little bit more complicated expression. So here we have A and B, and then D will be the multiplication of the 2, and E will be the addition of the 2. And then we multiply E times D to get F, and then we call it F.backward. And these gradients, if you check, will be incorrect. So fundamentally what's happening here, again, is basically we're going to see an issue anytime we use a variable more than once. Until now, in these expressions above, every variable is used exactly once, so we didn't see the issue. But here, if a variable is used more than once, what's going to happen during backward pass? We're backpropagating from f to e to d, so far so good, but now e calls it backward, and it deposits its gradients to a and b, but then we come back to d and call backward, and it overwrites those gradients at a and b. So that's obviously a problem. And the solution here, if you look at the multivariate case of the chain rule and its generalization there, the solution there is basically that we have to accumulate these gradients. These gradients add. And so instead of setting those gradients, we can simply do plus equals. We need to accumulate those gradients. Plus equals, plus equals, plus equals, plus equals. And this will be okay, remember, because we are initializing them at 0. So they start at 0, and then any contribution that flows backwards will simply add. So now if we redefine this one, because the plus equals, this now works. Because a.grad started at 0, and when we call b.backward, we deposit 1, and then we deposit 1 again, and now this is 2, which is correct. And here, this will also work, and we'll get correct gradients. Because when we call e.backward, we will deposit the gradients from this branch, and then we get to d.backward, it will deposit its own gradients. And then those gradients simply add on top of each other. And so we just accumulate those gradients, and that fixes the issue. Okay, now before we move on, let me actually do a bit of cleanup here and delete some of this intermediate work. So we're not going to need any of this now that we've derived all of it. We are going to keep this because I want to come back to it. Delete the 10H, delete our harmonic example, delete the step, delete this, keep the code that draws, and then delete this example and leave behind only the definition of value. And now let's come back to this nonlinearity here that we implemented, the 10H. Now I told you that we could have broken down 10H into its explicit atoms in terms of other expressions if we had the exp function. So if you remember, 10H is defined like this, and we chose to develop 10H as a single function, and we can do that because we know its derivative and we can backpropagate through it. But we can also break down 10H into and express it as a function of exp. And I would like to do that now because I want to prove to you that you get all the same results and all the same gradients, but also because it forces us to implement a few more expressions. It forces us to do exponentiation, addition, subtraction, division, and things like that. And I think it's a good exercise to go through a few more of these. Okay, so let's scroll up to the definition of value. And here, one thing that we currently can't do is we can do like a value of, say, 2.0, but we can't do, here, for example, we want to add a constant 1, and we can't do something like this. And we can't do it because it says int object has no attribute data. That's because a plus 1 comes right here to add, and then other is the integer 1. And then here Python is trying to access 1.data, and that's not a thing. And that's because basically 1 is not a value object, and we only have addition for value objects. So as a matter of convenience, so that we can create expressions like this and make them make sense, we can simply do something like this. Basically, we let other alone if other is an instance of value, but if it's not an instance of value, we're going to assume that it's a number, like an integer or a float, and we're going to simply wrap it in value. And then other will just become value of other, and then other will have a data attribute, and this should work. So if I just say this, redefine value, then this should work. There we go. Okay, and now let's do the exact same thing for multiply, because we can't do something like this, again, for the exact same reason. So we just have to go to mul, and if other is not a value, then let's wrap it in value. Let's redefine value, and now this works. Now here's a kind of unfortunate and not obvious part. A times 2 works, we saw that, but 2 times A, is that going to work? You'd expect it to, right? But actually it will not. And the reason it won't is because Python doesn't know, like when you do A times 2, basically, so A times 2, Python will go and it will basically do something like a.mul of 2. That's basically what it will call. But to it, 2 times A is the same as 2.mul of A. And it doesn't, 2 can't multiply value. And so it's really confused about that. So instead what happens is in Python, the way this works is you are free to define something called the rmul. And rmul is kind of like a fallback. So if Python can't do 2 times a, it will check if by any chance a knows how to multiply it too, and that will